Hello, everyone. First of all, thank you all for coming to tonight's ASDRP Blitz Talks, and we'll be presenting tonight our research on human pose estimation. First of all, hopefully you all can see my screen. Let me know if you can.
Yeah, we can.
I think you can. Okay, that's awesome. So as I said, today's research is on human pose estimation, and our research included us analyzing methods to classify both correct and incorrect postures. This was done by me, Kushagra, and
Niranjana and Shivi.
First, throughout this presentation, we'll be discussing first the introduction to what human pose estimation is, then we'll be talking about the data collection process, then we'll be moving on to the model, and then finally we'll be talking about our future steps. First, we'll be talking about what human pose estimation is, some of the previous research done in HPE, what image annotations are, and also our personal research focus. So what exactly is human pose estimation? Well, human pose estimation consists of a task of computer vision that focuses mainly on detecting, associating, and tracking joints of the human body. This can be applied to many different areas of fields, such as determining the risk of injury in many cases, such as sports, classifying the correct form of posture in various activities, as you'll be seeing later in this presentation. We did for planks, but also in cycling, walking, and etc., and also motion tracking. To understand how human pose estimation works, it uses image annotations. Well, what are they used for? Image annotations are used in the process of what we call labeling the image. The annotations, as we can see by the colored dots in the far left picture, they capture a set of joints, which we call key points, which are used to determine the pose of a person. The points are connected to form what we call pairs, creating a skeleton-like representation of the human body. Personally, we used image annotations in the pre-processing images for our model. For previous research done in human pose estimation, the first usage was in head pose estimation for determining face alignment. This was often used in many fields such as the original face identification. Then the second type of previous research was in video pose tracking, where it was used for determining various poses through videos, then also in surveillance, in security cameras, for example. And finally, today is being used in action prediction. This is where you predict poses and also future actions. So for our research, we decided to focus on what was the best way to classify both correct and incorrect pose postures using human pose estimation. We focused on two different methods. First, we focused on testing current methods on data, and second, we fine-tuned models to improve our performance.
All right, so let's talk about data collection. We're going to be talking about what we considered correct posture. We're going to be talking about examples of correct and incorrect posture, and we'll look at some examples from our data set, what we needed for data collection, where we got our data, our sources, and finally, how we pre-process the data. So what do we consider correct posture? So the plank is one of the most popular exercises, but it's also one of the most common exercises that people get wrong. Completing this exercise wrong can cause severe injury to several parts of the spine, including the thoracic and lumbar spine. Therefore, what do we consider correct posture? According to fitness experts, there are several components of a correct plank. The legs should be straight with the knees off the floor. The spine or back should be flat and not curved. The hand should be directly underneath the shoulders at about a 90-degree angle, and the chin should not be tucked in. So now let's look at an example of a correct and incorrect posture using plank images from our data set. So on the left is an example of a correct posture. As you can see, the back/spine is flat. The knees are off the floor. The arms at a 90-degree angle, and the chin is not tucked in. So we would classify that as correct posture. However, the one image on the right, the back is not necessarily flat. It's tilting upward. The knees are off the floor, but the chin is tucked in. So in this case, we would classify this as incorrect posture. Let's look at some more examples. So as Kushagra mentioned earlier, we use image annotations in our model. And so this is how it would look like. On the top left image, we can see a correct plank posture with the image annotations. We can see that the back slash spine is flat. There's a 90-degree angle formed with the arms and etc. However, on the top right, that's not necessarily the case. We can see that it's arching upward. So we'd classify that as incorrect plank posture. And the image on the bottom is a sort of a more realistic of how our data looks like. In this case, the subject has incorrect plank posture as their back doesn't form a straight line and the knees are still on the floor. Now let's talk about what we needed for data collection. We needed images of people doing the plank position both correctly and incorrectly. And we ended up using over 450 images to classify the plank postures into two classes, correct and incorrect form. We had about 200 correct form and formatting. It had over 25K images from 410 different activities. It's one of the most diverse data sets in human pose estimation. We ran through the data set, especially in the circuit training and gym photos, and we looked for correct and incorrect postures in plank positions. We added this to our training and testing data. The second data set we used is Kaggle Yoga Poses data set. Just a brief introduction, Kaggle is a data set library owned by Google. For this specific data set, there were roughly 1,500 images and of yoga poses split into 70-30 training testing distribution. We extracted the plank images from this data set and put them into our two classes. And lastly was the COCO data set, the Common Objects and Context data set, and it's a complex data set consisting of both videos and pictures. It was created by researchers from Google, FAIR, and some other college researchers as well. We downloaded a portion of the images and then scanned the plank images for correct and incorrect posture. Next slide. So how do we pre-process the data? There's four main things we needed to do. First, we needed to resize the images. Since the images were from 3 different sources, we need to resize them for our model. In order to do this, we used OpenCV's resize function, and we resized all images to a smaller square, and we tested with 3 different sizes, 512 by 512 pixels, 224 by 224 pixels, and 100 by 100. And 512 by 512 pixels resulted in the best performance from our model. Second, we need to cast it as a NumPy array. And in order to do that, we created a NumPy array of the pixel values with the 3 dimensions to account for color. Third, we needed to normalize the pixels. In order to do that, we divided it by 225 to represent the RGB values in a range from 0 to 1. Lastly, we need to label our images into our 2 classes.
Now on to the models we evaluated. First, we'll go over the libraries, some of the models we used, and how we evaluated them. Next slide. So some of the libraries we used were TensorFlow, OpenCV, and sklearn. TensorFlow we used as a model library that helped us create our deep learning models, especially the CNNs, as it provided methods for creating sequential models and layers. For OpenCV, it's used for computer vision problems such as ours, as it helps resize, crop, and pre-process the images for the model. And the sklearn library provides tools for machine learning, such as splitting, training, and testing data, and randomly shuffling them. And some of the models we are evaluated and are going to continue to evaluate are OpenPose, DeepPose, MoveNet, and CNNs. So for OpenPose, it has pre-trained models on other images to detect people's joints or from an image or video. As we mentioned earlier, it would draw a skeleton on the figure and then put that into the model and classify it from there. DeepPose is a similar approach and uses a deep neural network to do this, but instead of drawing a skeleton, it would instead output the coordinates of the joints on the image. Instead of drawing a skeleton, it would find the coordinates. And MoveNet is just one of TensorFlow's pre-trained model that does this task. And the ones we evaluated in this term were the CNNs, convolutional neural networks, where we use 3 layers and 2 layers just to deal with the raw pixel data from the images. And for evaluating the models, we mainly focused on accuracy, F1 score, and AUC score. For the accuracy, It just determined the accuracy of the model's predictions on test data. F1 score measured precision versus recall, which is more specifically on the model's performance of predicting each class. And the AUC score is a similar measure that measures the model's ability to distinguish between the classes. And most importantly, to help visualize the F1 score, we outputted a confusion matrix for each model. And for results, when we evaluated the CNNs, we saw that a CNN with 2 layers actually performed better with the 93% accuracy versus one with 3 layers, which performed with 89 accuracy. And for the best image size, we determined that 512 pixels by 512 pixels actually performed by far better with over 10% accuracy compared to 224 or 100 pixels. And surprisingly, images with color performed better by around 15% than when we converted the images to black and white. And here is one of our figures. That's just a confusion matrix for the model with 3 convolutional layers. And it just shows the model's predictions of when it was accurate and inaccurate. And for future steps, we're going to continue testing the other models we mentioned earlier and see if they perform better than the CNNs. And also we can continue to evaluate different data, not just playing postures, but other postures used in exercises, yoga, and any other sport to see if it's in the correct or incorrect form. And thanks for listening. We'd like to acknowledge Mr. Subramanian for guiding us through the project and ASDRP for providing us for the resources. Thank you.